Hi everyone. In this session, we are going to solve a specific problem solving question. This is the question. We are given an unsorted array and we have to find the kth largest element. In the previous series, we have seen that this can be done by several ways. We can sort the array and then we can solve it. We can use a recursive logic called getMax, and then we can keep track of how many times this has been called. So if I have to find the third largest element, I have to call getMax 3 times, and in the recursive logic, I have to address the parameters. We can also use a map as well. We can use a map. Basically, what we can do is iterate through the array. We are given the unsorted array, let's call it ARR, and then we can move through it, find the max, put it in the map, remove from the array. Find the max again, put it in the map, remove from the array, and so on. So the key value pair, what would be the key? Let's say the key will be the number itself, or I can say index, and the value will be number. So it will be something like first largest, let's say the number is 10, second largest, the number is 20, third largest, the number is, let's say 30, and so on and so forth. So once the map is populated, we can see what is k. So k will be one of these values, right? First largest, second largest, third largest, whatever k is corresponding to that key, we can return the value stored inside the map. So these are all the ways that we can use. In this method, in this specific session, we are going to use a variation of Quicksort. So if you don't know what Quicksort is, that's okay. We are going to basically cover Quicksort as well. And by the end of this session, you will be knowing how does Quicksort operate. It's not exactly Quicksort, but a variation of Quicksort. Other methods, how to like sort the array using our custom implementation. We are not going to use any inbuilt method, using our own sorting implementation. That is how in interviews as well, you are not allowed most of the times to use inbuilt methods. They want to test your logic. So you have to basically implement all the things from scratch. So for these things, how to sort it using our custom sorting implementation and then return the kth largest, or how to use the recursive call. These are there in the playlist series. So if you can like go back to the same playlist as this video and examine the initial videos, there are solutions for these. In this, we are going to use a quicksort variation. So let's quickly examine. Let's say our unsorted array looks like this. Any random values, let's say 10, -1, 40, 41, and let's say 5. Right. So if this was the array, let's have one more element. So had this array been sorted, it would be looking like -1, 5, 6, 10, 40, and 41, right? We're not going to sort the array, but had this array been sorted, it would be like this. And from this array, if I have to find, let's say the k is given to us as 2. So basically what I'm saying is give me the second largest element. So from this, we can easily see that the second largest element is what? The second largest element is, let me quickly use the highlighter, this guy, 40, right? Forty is the largest, and the second largest is quickly connect my touchpad. For some reason, it stopped working. Now it is back. So this is the first largest. Last element, once the array is sorted, will be the first largest. And second last element will be the second largest, and so on. So we're not going to sort the array, but this is just for understanding. Now, how does Quicksort operate? Quicksort operates basically by having some pivot element, and then once we have the pivot element, everything on the right of the pivot element will be greater than P, and everything on the left of the pivot element will be less than P. Right? Let's try to operate it, and then it will become all the more clear. Let's have the pivot element as the last element of the array. So we are going to have the pivot as 6. Right? This is the pivot element. And then what we are going to do, we are going to start some operations so as to partition this whole unsorted array around the pivot element. So everything on the left of the pivot element would be less than that, and everything on the right of the pivot element would be greater than that. What we are going to do is we are going to run a few loops. So if I have to write some pseudo code, it would be something like this. For int, basically, I'm going to traverse from L to R, from L to R minus 1. What is L and what is R? Basically, these are left and right pointers. And left, I can start with ARR of not the value, but the index. Left can be 0, right can be the last index, right? The last index will be ARR of length, ARR dot length, not of, my bad, ARR dot length minus 1. So this will be the last left one, and this will be the right one. And we are also going to maintain a pointer, a pivot pointer that we are going to keep track. So it will start with L. So the pivot pointer is also going to start from here. So then what we are going to do inside this for loop, once we are iterating it, let's call it I. I is going to be from L to R minus 1. And let's have some comparisons going on. So what we're going to compare is ARR of I. Is it less than or equal to the pivot element? That is my comparison. So 6 is the pivot element. Is 10 less than or equal to 6? No, that's not the case. So if that's not the case, we will not do anything. Otherwise, we will keep moving. Right? So this I is basically progressing ahead. Initially, I will be at, we call it, let's use the blue. So initially I will be at starting from L, right? And this case is not met, 10 is not less than 6. So it will be not here, and I will come here. And what about ARR of I? In this case, ARR of minus 1. So minus 1 is less than the pivot element, which in this case is 6, right? So this meets the condition. So if that is the condition, we are going to swap what? ARR of I with the ARR of P. This is what we are going to do. So what this will do, minus 1 and 10 will be swapped. So 10 will be here and minus 1 will be here, right? So why is this swapping done? So what basically what we are doing is we are comparing each and every element to the pivot. So 10 is compared to 6. If 10 is greater than 6, we don't do anything. Then if minus 1 is greater than 6, right? So the pivot pointer P is going on from 10, minus 1, 40, 41, 5, and 6, and so on. So pivot pointer was initially at this value. And then this pivot pointer, whatever element it was pointing to, that was not great. That was not less than or equal to 6. So nothing to bother about. So next time the I counter came from 10 to -1. -1 was indeed less than or equal to 6. So that met the condition. So if that met the condition, we are going to swap ARR of I and ARR of P. So this is -1 and ARR of P was pointing out to 10. So -1 and 10 are swapped. So after swapping, it will look like this, and the rest of the things are going to remain the same. And one more thing we have to do, once we have done that, we have to increment the pointer as well, the P pointers, so that the P pointer does not lag behind. It is going to not here, but now it will be pointing to here. And then this index will move ahead. So index I will come here because of the virtue of this loop, right? And then again, same operation. Is 40 less than or equal to 6? No, that's not the case. So again, this is not met. I comes here. What about 41? Is it less than or equal to 6? No, that's not the case. So I keeps moving without executing this condition. What about this case? ARR of I, that is ARR of I in this case is 5. 5 is less than or equal to 6. We're always comparing to the pivot element. Yes, 5 is less than 6. So this condition is again met. So we are again going to swap ARR of I and ARR of P. So 10 will come here and 5 will go here. Right. So, and we are going to increment the P pointer. So P pointer will be incremented to here. What after this? Now we have got this, and our loop, that is I, is running from L to R minus 1. Right. So R is at this position and we have reached 1 minus, right? So we have reached whatever was the complete iteration. So once we have reached it, what we are going to do is, let me choose the pen. Once we have reached this, we are going to swap whatever is we had performed to. We're going to perform another swap, and this time the swap is going to be the pivot element itself. The pivot element itself. I should say not the pivot element, but I should say better way to write it correct is ARR of R. That will be swapped with ARR of P. So if you notice, 6 is there and this is there. So this will become 6 and this will become 40. And now you can realize why we are doing all this. It will become all the more clear because now you can see this is P, right? And if you examine things on the right of the P here, everything on the right of the P, 41, 10, and 40 is greater than ARR of P is greater than 6, and everything on the left of P, right? That is -1 and 5 are less than 6. So this was our original pivot 6, right? The pivot has reached this right position, and everything on left of the pivot, that is -1 and 5 are less than 6, the value of the pivot element, and everything on the right of the pivot element 6, that is 41, 10, and 40 are greater than 6. One key thing to remember is like these elements, like these subsets. This can be one sub array, and this is a sub array on the left of the pivot element, and this is a sub array on the right of the pivot element. Both of these sub arrays, these itself are not sorted, right? It is just a coincidence that -1 and 5 appear sorted, but there is no guarantee that it is sorted. Similarly, on the right hand side sub array, the right side of the partition, right? It is not guaranteed. 41, 10, and 40 are not sorted among themselves. The only thing that is guaranteed is all the elements on the left of 6 will be less than 6, and all the elements on the right of 6 will be greater than 6. And now what we need to do, we need to check if we have met the condition or not. So the condition that we are going to check is we are basically going to compare K and P. What this current value of P tells me that where have we reached in order to find the kth largest element, what position have we reached. So if I have to simplify, one more thing that is going on right now here is, if you notice, if I have to find the kth largest element, let's say k is equal to 2, I am getting this 2 when operating from the back, right? So my answer should be always from the front, because that is how the arrays are. Indexes always starts from 0, 1, 2, 3, 4, and 5. So technically, if I have to say that give me the second largest element in this array, had the array been sorted, I would have found the second largest, but not from the front, from the end. And then the question comes, what would be the index right from the beginning? So if you count from the beginning, not the position, but the index, this is the right answer. It would be the fourth index, right? Fourth index. And how did I get the value of 4? It is basically 6 minus 2. And if you have to generalize this is nothing but AR dot length. What is 2? The provided value of K. So this is the generic formula AR dot length minus K. So 6 minus 2, 4. So basically I'm saying give me the fourth smallest element. This question, give me the second largest element, can be reframed as give me the fourth smallest element, because the second largest element is indeed the fourth smallest element. The first largest element is the first largest element is the sixth smallest element. So in order to make our computations a little bit easier, right in the beginning itself, we could have done that thing. So we could have rightly said that K is equal to, let me write it here, AR dot of length minus K. So let's say the K is 2. So length is 6. 6 minus 2 is 4. So now I am interested in returning the whatever the values is present at the fourth index. So in this case, 40 is the answer, right? This array is not sorted, but if you notice, this was the original array, 10 minus 1, 40, 41, 5, and 6, right? And in this original unsorted array, if the question was give me the second largest element, the answer would be 41. So it's same way as saying as give me the fourth smallest element. So whether I ask the second largest element or the fourth smallest element, the answer is the same. This computation will make our life a little bit easy. And then 41 is what should be our expected answer if the value of K is 2. So second largest or fourth smallest. So coming back to this program, we are now in a position to compare K and P, K after adjustment. So 4 is there, and what is the current value of P? If you notice, the current value of P is 2. 0, 1, and 2, right? At the end of first iteration. So they are not equal. If they're not equal, 3 conditions. In this case, they're not equal, but in general, when the program runs, three things can happen. Either K becomes equal to P, or I could have said is K is less than P or K is greater than P. So if K is equal to P, let's say I was asked, give me the fourth largest element. So fourth largest element, in that case, fourth largest element. So K would have been 4, right? And K after adjustment is 6 minus 4. That is length of the array minus K, that is 2. Or give me the fourth largest or second smallest element. That's the same thing. Fourth largest or second smallest element, and the answer in that case would be 6, right? If you notice the original array, right? 1, yeah, the index would be that thing. So in that case, we would have reached it. So if you examine 6 here, 6 in this case is the fourth largest element, right? 6 is the fourth largest element. So we have reached what we wanted here. In this case, K would have become equal to P, because K is also 4 and P in this case is 2. So if that is the case, if the provided value of K is matching it, so initially it should be equal to P. And if that is the case, we have reached what we wanted. We have to simply return ARR of P. If that's not the case, then we have to call this program recursively. So if that is the case, K less than P, we have to think about left partition. Otherwise, you have to think about right partition. So what we are going to do, if that is the case, if K is less than equal to P, we are going to call this method, let's say my method, recursively. And all this, imagine that all this logic is going inside my method. So I have a my method, and here I am writing all the logic there. So this my method is going to be called recursively after adjusting for the parameters. So we'll have some parameters, basically left and right. Originally, the my method was called with left and right parameters, right? Left was 0 and right was the last index. So last index is always AR of length -1. Now I'm going to, if I'm going to talk about left partition, let's say this is the left partition. And let's say this would be the right partition. The concept is going to be the same, just a recursive call with adjustment of left and right would be made. So P is determined. This is the left, this is the right. And I'm going to keep 0 as same, but the right one will be P -1. What about right partition? Again, recursive call to my method using P +1. And the last index is going to remain the same. Right? So this is how the logic in general will operate. If we examine our situation where we have reached, in this case, while we are comparing K and P, we are seeing that K is ahead of P, right? K is ahead of P. So if that is the case, we have to examine the right partition. In the right partition, this is the right partition. Let me see if I can highlight it. This is the right partition, right? This is the right partition, 41, 5, and 6. So now we have to recursively call the program in 41, 5, and 6, and the concept is the same. So if I write 41, 5, and 6, the same operation is going to be performed. Left is what? Left was P +1. So P was 6. So 6 + 1, 7. I can write here itself. Let's say left here and right is going to remain the same. This loop is again going to be running from, this time it is going to run from I is starting from here, and then it will keep moving here. So again, we are going to have the pivot element. The pivot element is no longer going to be 6. The pivot element is going to be 40 now. The last element is what we keep as the pivot. And then we are going to run this loop I from L to R. This is left. This is left. This is I. This is P. Everything starts from here. This is right. And then we are going to make this comparison again. Is ARR of I less than equal to pivot? So 41 is less than equal to 40. That's not the case, right? So I will keep incrementing, keep moving ahead. Is 10 less than 40? Yes, 10 is less than 40. So in that case, we are going to swap this 10 with whatever the pivot is, with whatever is ARR of P. So 10 will come here and 40 will come, 41 will come here. Right? And then this iteration of I is only going to run till this much. So this has ended. And then we are going to move to the next iteration. After swapping the swap ARR of R and ARR of P. So ARR of R is 40 and P after being incremented is here. So we are going to swap 40 comes here and 41 comes here. So now you can notice that everything on the left of 40 is less than 40 and everything on the right of 40 is greater than 40. It's 41. So now another iteration has been completed, right? And now you can see what is the value of P. The value of P is, if you notice the index 0, 1, 2, 3, 4. So this is a condition where we have met this rule. The value of P in this case will be 4, which is equal to K. So 4 is equal to 4. So we have reached what we wanted. We have to simply return whatever is there at the index that is stored here. So the answer is always going to be returning ARR of P. Right? I have to recursively call this method by this left partition. For the right partition also, I have to recursively call this method. And what if it is equal? If it is equal, I have to simply return ARR of P. In this case, K is equal to P, so I will be returning ARR of P. So in this case, it is equal. So ARR of P or K is whatever it is, 4. And at the fourth index, you notice 0, 1, 2, 3. So what this was the original, right? So 0, 1, 2. And I'm going to get 0, 1, 2, 3, right? 41 is what I'm going to get. Because where is it? Yeah. So second largest element is what I wanted, or the fourth smallest element is what I wanted. So right now I am going to be returned 40, right? P is here at this point of time. So returning ARR of P is this case, ARR of P index. Let's keep it like this. Wherever P was at this point of index, and at that point of time, P also become equal to K. Right? K was 4, P was 4. So if that is the condition, in this condition, we are going to return ARR of P. So ARR of P, whatever is the P pointer, that is going to be returned. So P pointer is here, 40 is this value, and 40 is going to be returned. So the answer would be 40, right? 40 is returned. And this is the correct answer. So if you notice this array, the second largest element, this 41 is the first largest element. And 40 is indeed the second largest element. So 40 is the answer, second largest element. Why we are saying 4? Because it's also the, in terms of index, 0, 1, 2, 3, 4. In terms of index, fifth smallest in terms of value, or fourth smallest in terms of index. So that is the answer. And second largest element is 40. This we have got it. So this was the explanation. If you're able to understand this, you should be able to code it out as well. We are doing nothing fancy, but creating some pointers left, right, P, pivot element. Then we are running a for loop. We are creating a simple method name, and inside this method name, we are writing all the logic, initializing all the pointers, creating a for loop that runs from, that has a placeholder value I that runs from L to R minus 1. And in every recursive call, we are adjusting the left and right pointers. Inside the for loop, we are checking if ARR of I is less than equal to pivot. If it is, we are performing the swap and then incrementing the pivot pointer. Otherwise, we are doing nothing. When this for loop ends, we are doing the final swaps of the pivot element with ARR of R. The final swap of the pivot element with ARR of R. And once this has been done, we are trying to calculate whether we have reached our goal or not. If K is equal to P, we have reached our goal, we can simply return ARR of P. So that is the exit condition of the recursive call. If that's not the case, two conditions are possible. Either we have to recursively call the left partition if K is less than P, or if K is greater than P, we have to recursively call the right partition. So in insertion sort, we are sorting the whole array. So we have to run the recursive call for left partition, which in turn will repeat the same process. And as well as we have to run the recursive call for the right partition because we have to sort the whole array. But here we are not needing to sort the whole array. We are only interested in finding the kth largest element. So the kth largest element will be P itself, wherever P is pointing to, or lying to the left of it, or lying in the right partition. So whatever is the value of K, we can compare it with P, and then we can know whether it is in the left side or the right side. So only one partition, either of one of these, needs to be solved. And that is why it is called a variation of the insertion sort method. In terms of code, how it is going to look like, I've already coded it out for saving some time, but this is what it is going to look like. We are given any unsorted array. This comment I've written just for seeing what would be the answer. The same values are there pretty much. In this case, if K is equal to 2, that is, I'm interested in the second largest element. The answer should be 39. 39 is indeed the second largest element, right? So I'm adjusting K again, just to simplify some calculations. The second largest element is also the fourth smallest element or fifth smallest element, right? 1, 2, 3, 4, fifth. So the second largest element is also the fifth smallest element. Why fifth? Fifth in terms of position. If I have to talk about in terms of index, since index always starts from 0, 0, 1, 2, 3, 4. So the second largest element would be whatever element is stored at the fourth index. That is how I'm getting the index 4 here. ARR dot of length minus K. Length is 6. 6 minus K, that is 2. 6 minus 2, that is 4. So after adjusting the value of K, since it's static, it is adjusted throughout the context of the program, throughout the scope of the program. It's a static global in this case. Once I've adjusted for K, then I've called the myQuicksort method, got the return value and printed it out. This is where the meat of the logic is. Calling of the definition of the myQuicksortVariation method. All we are doing, bothering about two pointers, left and right. During the first invocation to the method, left is 0 and right is the last index of the array, which is ARR of length minus 1. And then we are getting the pivot. For ease, we are always keeping the last element as the pivot. So whatever element is stored at the right index or ARR of R, that is the pivot. The pivot pointer or P, this pointer, pivot pointer, we are initializing with L. So it's always going to be whatever is the value of L. So in the first call, L is 0. So P is also going to 0. And we are basically running a loop. I is less than R, right? So 1 less than the index value stored in R. So from L to R minus 1. So in this case, from 0 to second last element, because the last element itself is the pivot, we don't want to compare with it. That is why from 0 to the second last element, we are running this for loop. Inside the for loop, we are doing the same check. If ARR of I is less than equal to pivot, if it is, we are swapping ARR of I with ARR of P. So these three statements are doing nothing but the swap of ARR of I with ARR of P. ARR of I and ARR of P are swapped. And once the swap is performed, we also need to move the pivot pointer ahead. And that is why plus plus P. And once the iteration, the for loop has been covered, we are swapping ARR of R with ARR of P, right? And once this swap is performed, we are checking if K is equal to P. We have got it. We have got the result. We can simply return ARR of P. If that's not the case, we have to examine the left partition or the right partition, one of them, right? But not both, any one of them. And that examination is done by recursively calling the same method, myQuicksortVariation, with adjusted parameters. So if I'm calling the left partition, left will be 0, but right will be 1 behind the current value of P. So at the end of this whole process, whatever the P's value is, 1 less than that, P minus 1, that would be the right index. The left index would be 0 only. The right index will be 1 less than P. That is the parameters for left recursive call. In the right recursive call, that is examining the right partition, the last element, the ending point is always going to remain the same, that is R, but it will start from 1 ahead of P plus 1. So exactly same thing as what we are doing in code, right? We are running this for loop, doing the comparison, swapping, increasing the P pointer. And once this for loop has been finished, we are swapping the ARR of R with ARR of P. Whatever is present at the pivot pointer, that element is being swapped with whatever is stored at the R. And then we are comparing the value of K and P. Either we have got the result, or we have to call the left partition recursively, or we have to call the right partition recursively after adjusting the parameters. For left, it will be P minus 1. For right, it will be P plus 1. So that's it. At some point of time, this program will end because this condition will be met. And when this is met, I'm getting the answer. Let's try to quickly run the program. Right, the second largest element is 39, which is correct. If you examine this original unsorted array, this is just for reference. And if you refer to this, second largest element means second from the last, that is 39, which is correct. That is the correct answer. That's it, guys. So this is often asked in interviews. There are several variations of doing this. We can use max heap or min heap, that is heapify solution. We can use recursion, where we can repeatedly recursively call the get max method, or we can use the map based method. That is also one method. I think these are the methods where I'm basically sorting it out and then solving it, or I am using the recursive call to the get max method, then solving it, or I am using a heap. So in Java, behind the scenes, it's a priority queue that implements the min heap. So I can follow that. There are videos for all these three approaches. Right now in this video, we're talking about this approach, and according to this approach, my quicksort variation, we are getting the answer as well. So that's it, guys. That's it for this video. For further videos, if you like our channel, please do like and subscribe to the channel and hit the bell icon for getting all the notifications. Other things are there on the website, zboard.com. For any queries, please feel free to contact us by the North American contact number or the Indian contact number. And we provide different services from individualized to group training, entry to software, IT jobs, interview as a service, software training, consultancy, project development, staffing, recruitment services, as well as a mock interview and preparation calls. So whether you are a student looking for entry into software development, or just to hone or sharpen your DSA skills, or you are an employer looking for some recruitment services, consultancy, staffing services, please feel free to contact us by zboard.com or at these contact numbers. That's it, guys. Thanks for watching, and let's meet in the next video. Thank you.